Hi, welcome to Random Walk with Varying Step Size, Take 2. In this series, we're trying to gradually build up an intuitive understanding of Gaussian measurement errors through a series of random walks. As usual, let's say we're measuring some quantity in nature. When we do the measurement, we'll get some result, which we call Q measured. And Q measured will not be exactly the same as the true value of that quantity, which we'll call Q true. This is because there will be, typically, many sources of error which will cause Q measured to differ from Q true. So here we represent these error sources as yellow arrows which push Q measured up or down from Q true by various amounts. We previously said Gaussian-like measurement errors tend to arise when the lion's share of the error is dominated by a set of many, or at least several, independent error sources. Those sources on average don't have a bias to push Q measured up or down, and those sources have similar typical sizes to each other. In our first attempt, we made a very simplified model of these error sources. We took there to be n important error sources, and we took them all to have the same size, but allowed their direction, up or down, to randomly vary from trial to trial. So our expression for Q measured was approximated as Q true plus a set of equally sized errors represented by arrows of all the same length. We then calculate the sum of these n sources by simulating an n-step random walk simulated by having balls fall into bins after a series of n steps. Here are the probabilities of the location of the ball after 5 and 15 steps. It's a little hard to describe the n equals 5 result as Gaussian, but we can see the shape of the curve for n equals 15. So we could see that Gaussian-like behavior arises as n gets large. Then we made a second attempt. Here we tried to address the fact that having the error sources always be exactly the same size, like in our first attempt, was not very realistic. So we let the step size vary from trial to trial. We upgraded the model to have step sizes be the same only on average. The size of a particular step in a particular trial was chosen from a flat distribution between -1 and +1. Here are what the results look like for n equals 3 and n equals 5. Our simulations using 5,000 balls are at the bottom. The results at top use much larger statistics. We can see here for this varying step size random walk, the results are much more Gaussian. The resemblance to a Gaussian curve in red is clear even for n equals 3 and n equals 5. So, in our second attempt, Gaussian behavior was evident, even for n equals 3 and n equals 5, which are not large numbers. This model still wasn't suitable to describe most measurement error scenarios, as in most cases we don't have all of the important sources of error being the exact same size, even on average. But we were able to apply it to a somewhat realistic example involving rounding error. Now, we said before that Gaussian-like errors arise when the main sources of error have similar typical sizes. In our first attempt, we modeled this with a random walk where all the steps were the same size. And in the second, the steps were all the same size on average, but not the same size from trial to trial. Here, we're going to relax the requirement that all of the errors have the same typical size. And we're going to see the Gaussian approximation break down. There are two reasons to do this. First, in practice, error sources do not have the exact same typical size. This brings our model closer to reality. Second, seeing how the Gaussian picture fails gives a better idea of how well it applies to different cases. and taking those two reasons together, this will give us a better idea of how well the Gaussian description works in reality. So here we will again look at a random walk with varying step size. The step size will again be randomly taken from a flat distribution, but that distribution will not always be from -1 to +1. We will always set the number of steps n equal to 5. Now, this still isn't an adequate description of a typical measurement error scenario, as errors are not typically flatly distributed between two endpoints. But in the next video, we'll apply this model to a variation on the rounding error example that we saw previously. Okay, let's briefly look at our setup. It will help to remind ourselves of what we did for the n equals 5 case before, where all the steps had the same average size. A screen grab from our simulation is shown at right. The different colored ranges in the top half of the simulation showed the possible range of the ball at each step. All 5 steps had the same maximal size of 1 unit. At each step, the ball could move a maximum of 1 unit to the left or right. So the range increased by 1 on each side at each step. Thus we end up with the range at each step defined by this triangle shape. Under these conditions, we saw rather Gaussian-looking behavior. Now we'll do some examples where the different steps have different maximum sizes. We will always take there to be n equals 5 steps. In order to compare with our previous result, we'll always have the maximal step sizes for a run add up to 5. So the final location of the ball can be anywhere between -5 and +5. And in our simulations, we'll always drop 5,000 balls. Here are the 4 examples we'll be comparing. Here we list the maximum step size at each step. So for example, if a certain step has a maximal size of 1.5, that means the ball at that step can move up to a distance of 1.5 units left or right at that step. In these 4 examples, we will be progressively moving from the case where all the steps have the same average size, which is what we did before, to the case where one step has a much larger average size than all the others. So first, we have our previous result, where all the steps had the same size on average. Every step had a maximum possible size of 1 unit. Next, we have example 1. Here, all of the maximal step sizes are not too different from 1. 2 of them have a maximal step size of 1.5. 1 has a maximal size of 1, and 2 have maximal step sizes of 0.5. Next, in example 2, we have 2 steps that are, on average, quite a bit bigger than the other 3. And lastly, in example 3, we have a case where the first step is typically much larger than all of the others. Note in all of the examples, the maximal step sizes add up to 5. Okay, to see what we're going to do here, let's look at the setup for example 1. Here's what the simulation screen looks like to start. Like before, the colored regions at top demarcate the possible range of the ball at that step. Here we show how the possible range increases at each step. Because the maximal step sizes are no longer all the same size, the envelope of all possible ball paths over the 5 steps is no longer a perfect triangle. Okay, with that, let's get to our simulations. Example 1. Here, the maximal step sizes at each step are 1.5, 1.5, 1, 0.5, and 0.5, respectively. Let's drop 1 ball to see what happens. The largest step was the second one, where the ball went 1.075 units to the left. It ended up at the position x equals minus 2.033. Okay, now let's drop 5,000. If you watch closely, you'll see that the balls do typically move much farther to the left or right on the first 3 steps than they do in the last 2. Okay, let's speed up the process so it doesn't take so long. In the meantime, let's look at results obtained with much larger statistics and see if we can understand them. Here is the probability of a given ball ending up in each of the bins in the lower part of the screen. By eye, this looks pretty Gaussian, but let's plot a Gaussian on top of it. The Gaussian curve is now shown in red. It does look pretty Gaussian, but we can see deviations when the curve is overlaid. Let's compare this to our previous case where all the steps had the same maximal size of 1. Our previous result is shown at top. Our current result with different maximal step sizes is shown at bottom. While both distributions in blue show small deviations from the Gaussian curves in red, we can see that the deviations are a bit bigger in the current example. One might note that in our current example, we still have 3 steps that are of pretty similar size. There are 2 steps with size of 1.5 and 1 with a size of 1. The other 2 steps are smaller. So we might consider comparing this with the n equals 3 result that we had before when all of the steps had maximal size of 1. Here's what that plot that we made before looked like. Here, all 3 steps had a maximal size of 1. And the result is pretty Gaussian looking, although we can see deviations between the blue bins and the red curve if we look closely. So maybe it's not so surprising that our n equals 5 case here, with 3 steps of similar maximum size, also comes out looking pretty Gaussian. Okay, here are the results of this run of 5,000 balls. It looks reasonably Gaussian within our limited statistics. Okay, example 2. Here the maximum sizes for each step are 2.0, 2.0, 0.5, 0.25, and 0.25 respectively. Here we drop 1 ball. We can see that the first 2 steps were quite a bit larger in magnitude than the other 3, which makes sense. Okay, now let's drop 5,000. Again, we'll speed that up so it doesn't take so long. But in the meantime, let's look at what we will get for this setup with better statistics. Here's the probability for the ball to end up in each bin, and that does not look like a Gaussian distribution. Here we overlay a Gaussian distribution on the plot. The Gaussian gets the shape roughly right, but is definitely showing strong deviations from the contents of the blue bins. In fact, the shape looks kind of triangular. Let's see if we can figure out what's going on here. In this setup, we have 2 steps that are on average much larger than all of the rest, and they are of equal maximum size. Maybe we should look back at the n equals 2 case that we saw in our previous random walk, where every step had a maximum size of 1. Here's what that case looked like. When there were 2 steps, each with maximum step size of 1, the probability distribution of the location of the ball after the 2 steps was a triangle. Here, the first 2 steps have typical sizes much larger than the last 3, so while it doesn't happen every time, typically the ball will take 2 big steps and then 3 much smaller steps. The first 2 steps dominate, and the last 3 steps don't do much to the location of the ball. Okay, here are the results of this run. With these statistics, it's a bit difficult to visually judge whether the distribution looks like a Gaussian or a triangle, or somewhere in between. But it seems reasonable. Okay, finally, example 3. Here's the setup. The first step has a maximum size of 3, and the other 4 steps have maximum sizes of 0.5. We drop one ball. On the first step, the ball goes sharply to the left by 2.903 units. All the other steps are much smaller, and the ball ends up at minus 2.969. Okay, now 5,000. So here, one step has a maximum size that is much larger than the rest. We might guess that the result of the first step will largely determine where the ball ends up. Let's look at what happens with very large statistics. Well, that's an odd shape. It doesn't look like a Gaussian distribution at all. Since the first step here has a maximum size of 3, much larger than all the rest, we might expect it to dominate. What if we had just one step with a maximum size of 3? Let's compare our distribution with that. Here, the rectangle in red is the plot of the probability distribution if the ball only ever took one step, flatly distributed between minus 3 and 3. We can see that the two distributions are very close in the middle region, but differ quite a bit in the tails. After that first step, there are 4 steps which have equal maximum sizes. If the first step didn't exist, and only these last 4 steps happened, we would expect a pretty Gaussian-looking distribution for the location of the ball after these last 4 steps. So this distribution looks a lot like the ball took one dominant step of maximum size 3.0 and then exhibited small Gaussian behavior around the result of that first step. Another way of saying it is that after the first step, the ball's location is flatly distributed between minus 3 and plus 3, and the subsequent small steps smear that result out a little. Okay, here are the results for this run. It has a shape in line with what we saw with higher statistics. Okay, time for a brief discussion of what we've seen here. We've looked at 4 examples of random walks, 1 from our previous results and 3 that are new here. All 4 random walks had 5 steps. They all had varying step sizes, and the different steps had different sizes even on average. For each step, the step size was flatly distributed between 0 and a maximum step size. The examples progressed from the case where all the steps had the same average size to the case where one step dominated over all the others. Those 4 examples are listed here. Let's look at their results in sequence. Here are those 4 sets of results. First, we have our previous result, where all 5 steps had the same maximum size. It looks pretty Gaussian, although we can see deviations if we look closely. Next, we have our result of example 1, where we had 3 steps of similar maximum size and 2 steps that were, on average, quite a bit smaller. This is a little less Gaussian looking. The deviations between the red curve and the blue bins is more easily visible. Okay, next we had example 2, where the 2 steps dominated the rest. This doesn't look all that Gaussian. In fact, it looks more like a triangle, which is what we saw before for a 2-step random walk with steps of equal average size. And lastly, we have example 3, where 1 step dominates the rest. Comparing that result to a Gaussian is kind of laughable. So we saw here in this random walk, as a small number of steps begins to dominate the rest, the distribution of the ending point of the ball becomes far from Gaussian. When applied to measurement errors, this means that if a small number of error sources dominate the rest, the Gaussian description of measurement errors tends to fail. this is, unless those dominant error sources are themselves Gaussian distributed, a point which we'll try to come back to in a later video. In our next video, we'll try to link what we saw here more concretely to measurement errors. We'll apply the results that we got here to a scenario which is a variation on the rounding error example that we saw previously.